In Chapter 3, we're going to look at the math achievements of the Pythagoreans. The Pythagoreans discovered the irrational numbers like square root of 3, square root of 2, and so on. So the first type of problem in this chapter is to prove a given number is irrational. The Pythagoreans represent the numbers by the length of line segments. They also represented numbers by all kinds of shapes, like squares, pentagons, and so on. They constructed geometric representation of algebraic identities and geometric solutions of quadratic equations. At last, we're going to look at an example of transformation of areas. On page 83, the example is to prove square root of 2 is irrational. An irrational number is a number cannot be written as a fraction. If you had 306 before, then you probably have seen this example in that class. Instead of proving square root of 2 is irrational directly, we're going to prove square root of 2, we're going to prove it indirectly. We assume square root of 2 is rational by way of contradiction. So a rational number is a number that can be written as a fraction. Since we are assuming square root of 2 is rational, so we can write square root of 2 as a fraction of a over b. And we can pick numbers a and b such that they are relatively prime. Because if they are not relatively prime, we can find their greatest common divisor and divide them by the greatest common divisor. We will get a simplified fraction. For example, if we have 4 over 6, the greatest common divisor of 4 and 6 is 2. So we divide the numerator and denominator by 2 to get a simplified fraction 2 over 3. So it is possible to pick a and b such that they are relatively prime. And why are we doing this? We're trying to get a contradiction that a and b have a common divisor too. So it will be contrary to they are relatively prime. We multiply both sides by b to get a equals b times square root of 2, and square both sides to get rid of the square root. Left side is a squared and right side is b squared times the square root of 2 squared is 2. And 2b squared is an even number, and so a squared is also even. If a squared is even, then a is also even, because odd number squared is always odd. And an even number can be written as a multiple of 2. So we write a as 2 times another integer c. Replace a with 2c in this equation, we will get 4c squared equals 2b squared, and divide by 2 both sides to simplify it, we get 2c squared equals b squared. Similarly, because 2c squared is even, b squared is even, and if b squared is even, then b is also even. From these two conclusions, a and b are both even numbers, so they must have a common divisor too. But it will contrary to the assumption that they are relatively prime, which means they have no common divisor except 1. So this contradiction means our assumption is false. That means square root of 2 cannot be written as a fraction a over b. So it's impossible. That means square root of 2 is irrational. This identity we multiply it out a plus b times a plus b, we use for rule to get a squared plus 2ab plus b squared in algebra class. But the Pythagoreans proved it differently, because they, as we know, they represent all numbers by the shapes. So here, a squared corresponds to area of the square, a with each side equal to a, and b squared corresponds to the area of this square, b with each side equal to b. And these two blue rectangles with length a with b, the area of each one is a times b, so two of them will be 2ab. The right side can be represented by the areas of these two yellow ones plus these two blue ones, which form the big square with each side equal to a plus b, a plus b. And we check the left side. It's exactly the area of this big square. So both sides represent the area of this big square. That means we prove this identity by a geometric shape. Here is another example. We want to prove these two identities. In both graphs, AB is a line segment, P is the midpoint of AB, and Q is a point on PB, and here Q is an extension of PB. So we can think of P as a point that divides AB into two equal parts, AP and PB. And Q is a dividing point that divides AB into two unequal parts, AQ and QB. So the first identity means the two unequal parts, AQ times QB, plus the distance between two dividing points squared equals half of the distance AB squared. And the second one, because PQ is longer than PB, so we switch PQ and PB here and get the second identity. And we're going to look at the proof of the first one, and the second one will be the homework. From the last example, the product of two numbers can be represented by the area of a rectangle, so we try to construct a rectangle with length AQ, width AG equal to QB. So when we construct this rectangle, we make AG equal to QB. The first term on the left will be AQ times QB equals AQ times AG equals the area of the rectangle. And now we're going to construct PB squared and PQ squared. We construct a square PCDB such that PB equals PC. So the right side PB squared is exactly the area of the square. And now we're going to construct PQ squared. First we prove PQ equals HC. So these two blue lines are equal. Because this is a square, we construct PB equals PC. These two sides should be equal, so these two purple ones are equal. And also, when we construct this rectangle, we make AG equal to QB. And AG is also equal to PH because this is a rectangle. And we have QB equals PH. So these two red lines. And notice PB is divided into PQ and QB. PQ and QB. And PC is divided into PH and HC. PH and HC. And as we just proved, these two red lines are equal, so QB equals PH and these two purple ones are equal because this is a square. The left sides are equal, and on the right side, these two parts are equal, so these two parts must be equal. So we proved these two blue lines are equal. And we're going to use this fact to construct PQ squared. We extend HF to intersect BD, and we extend QF to intersect CD, and that's the graph. And we're going to show HCEF is a square, which is also equal to PQ squared. From the last slide, we proved PQ equals HC. So here, PQ equals HC. And also, PQ and HF, they are opposite sides of this rectangle, so they should be equal. So that means these three red lines are equal. And these two equal sides of this rectangle make it a square. And similarly, we can prove this blue one is also a square because QB equals QF. Why is QB equal to QF? Well, when we construct AG, we make it equal to QB, and AG is also equal to QF because this is a rectangle. So we have QB equals QF, and this is also a square. So now we are ready to prove this identity. The left side, we start from the left side. AQ times QB, as we constructed, is the area of this rectangle AGFQ. And the PQ squared is the area of HCEF square. And this rectangle can be split into two rectangles, AGHP and PHFQ. Here. And AGHP is equal to the area of PHLB because these two, the yellow one and this one here, have the same length, AP and PB, because P is the middle point, and the same width, AG and PH. So that means these two are equal. And then we look at a PHFQ. PHFQ, we're going to show these two white ones are also equal because FE equals, because this is a square, the blue one is a square, so FE equals HF and HF equals PQ. So we have two sides of this two white rectangles are equal. PQ equals FE. And also, this is a square, so FL equals QF. So we have the length of these two are equal, width of these two are equal, so these two white rectangles are equal. And if we look at these three, we add them together, the big rectangle PHLB plus the white rectangle FEDL plus this blue square HCEF is exactly this big square PCDB, and we can represent it by PB squared. So we proved our identity. And now we're going to look at the application of this identity. We're going to construct a geometric solution of a quadratic equation. This is a quadratic equation with A, B positive numbers. In algebra, we can use quadratic formula to find the solutions of X. The Pythagoreans did a different way. We construct these two numbers. So suppose we have 9 here, then we're gonna have B equal to 3, which is the square root of this constant. Suppose we have -7 here, we're going to construct a +7, a line segment, AB. And then we're going to find the midpoint of AB, denoted by P, and draw a vertical line segment EP, such that EP equal to B. And we're going to use a compass to construct a circle. Actually, we just need a little arc. We use E as the center and PB, which is half of the distance of AB, as the radius to draw a little arc intersecting PB at Q. We're going to claim AQ and QB are both solutions of this quadratic equation. This is the identity we just proved. And we move this to the right side by subtracting it. So we get AQ times QB equals PB squared minus PQ squared. And because when we draw this arc, we use EPB as the radius. So EQ is the radius, should be equal to PB. So we replace PB with EQ, the radius. And notice EQ is the hypotenuse of this right triangle, and the PQ is the one side. So by Pythagorean theorem, PEQ squared minus PQ squared should be EP squared, which is B squared. So that's why when we construct EP, we make it equal to B. And we get AQ times QB equals B squared. From this equation, we let AQ be x, then QB will be a minus x, because the total length of AB is a. Subtract this red part x, we will get a minus x for this little part AQB. So AQ is x, QB is a minus x, equals B squared. And we multiply it out, move B squared to the left, and multiply -1 to make the coefficient of x squared positive. We get the quadratic equation given. So that means this x, AQ, satisfies this equation, quadratic equation, so it is a solution. Then we can replace our x with a minus x, and replace this x with a minus x, and simplify it. A minus x times this part will be simplified to x equals B squared. And notice this is exactly the same as x times a minus x. So that means a minus x is also a solution of this quadratic equation. So this one can also be simplified to this quadratic equation given. So we proved this line segment, red one AQ, and this little one QB, they're both solutions of this quadratic equation. Now we're going to change my plus to minus and to construct another geometric solution. And here, we're going to use the other identity. AQ times QB plus PB squared equals PQ squared. Step 1, we're going to construct A and B like we did before, and find the midpoint P of AB. And this time, instead of drawing a vertical line at middle point P, we're going to draw a vertical line segment at B, such that EB equals B, and not like here. And instead of using this E as center, we're going to use the middle point P as the center, and PE as the radius to draw a line segment intersecting PB at Q. So we must have PE equals PQ. because they are both radius of this circle. Now, the left side, we're gonna subtract PB squared both sides to move this to the right side. And because PE and PB, they're both radius, so they are equal, we can replace PQ with PE. And the PE is the hypotenuse of this right triangle minus PB squared equals EB squared by Pythagorean theorem, which is B squared. So we get AQ times QB equals B squared again. And let AQ be X, because from A to Q be X, and then this little part of BQ will be X minus A, because from A to B is A. So we get our AQ is X, and BQ is X minus A, and the product is B squared. If we multiply out, we will get our quadratic equation equals 0 here. So we just showed our AQ satisfies this quadratic equation, which means it is a solution. And from these two quadratic equations, we can also construct our we can also find our solutions of these two quadratic equations. So we change minus minus to plus plus here. Notice if we have two solutions x1, x2 for this quadratic equation, then negative x1 will be a solution of this one, because negative x1 squared will still be x1 squared, but negative x1 times negative a will make a positive a times x. So if x1 is a solution of equation 1, then negative x1 is a solution of equation 3. Similarly, if x1 is a solution of 2, then negative x1 will be a solution of 4, because negative x1 squared is still x1 squared, but negative x1 times a will be a negative x1 times negative a will be a positive a times x1. Okay, now let's look at the last type, the transformation of areas. In this graph, we have AB parallel to CD. And so this is a parallelogram, and also AD parallel to BC. First, we look at these two triangles, FDC and HDC. Notice they have the same base, DC, and their third vertices are on the parallel line AB. So actually, it doesn't matter where this third vertex is. Could be here, here, anywhere on the AB. We can show the areas of this kind of triangle. These kind of triangles should be equal, because the area of a triangle is half of the base times the height, and they have the same base CD, and they also have the same height, because these two are parallel lines. The distance between two parallel lines are always the same. So we proved that these two triangles, they have the same base, same height. By the formula, their areas should be equal. And now let's look at a parallelogram. This parallelogram has the same base CD and the same height AE. But the area of a parallelogram is just the base times the height. So it's going to be twice of the area of the triangle. And we can use this property, so kind of like a transformation, because we can transform this area of this triangle to this triangle. So we can use this transformation to prove lots of properties. For example, in the homework problem, to prove Pythagorean theorem, So that's all for chapter 3.